All right, in this video we're going to take a look at resonant frequency, and particularly how it pertains uh, using inductors and capacitors. We've looked at both inductive and capacitive reactance. Well, first of all, let's get a circuit of some sort up here. So let's get our AC source. And there's generally some resistive component, so I'll put that in. And then we have some sort of capacitor, and then maybe we have a coil of some sort here. These are in series. Okay, so here's our R and our C and our L. And in terms of resonant frequency, we can pretty well forget about the R. It's going to be based on this. And I've put up here a little chart to show that when these two equal each other, that's when we get resonance. Notice that capacitive reactance is a curve. And this is our reactance up here, and on the that's on the Y scale. On the X scale here, we have frequency, a very low frequency for capacitors. We have very high capacitive reactance. It takes more time to charge up those plates. Okay. Whereas the inductive is pretty much the same rate of change because it's directly proportional to the change in frequency. As the frequency goes up, so does the reactance of that. But what's important here is this point right here where these meet, where these two values are equal. Well, there's a relationship for this. We could actually derive it from setting the two formulas for inductive and capacitive reactance to each other and then solving for F. And rather than waste video time of doing that, you can do that as an exercise. And that's a good exercise to do, by the way. I'll write it out here one time. We know that X sub L is 2 pi FL, and whatever that is, it has to equal 1 over 2 pi FC. And what we want to do is solve this equation for F. So this is a very good example. This really puts some sharp point on your algebra skills to be able to manipulate literal equations. We're not finding a numerical value. We're solving this equation for one particular variable, F. So you might start by multiplying both sides by this denominator to get rid of the fraction, and then start isolating for F. So there's a big hint for you on how to do that. All right, but we already have a formula that we know and love well. The resonant frequency is equal to 1 over our 2 pi. We can't get away from that 2 pi, or the 2 pi F. And this is times the square root of the value of the inductor times the value of the capacitor, the square root of that value. That will tell us, given a particular value of inductor and capacitor, at what frequency it will be resonant at. Okay, why do we want resonance? We get a maximum transfer, like matching impedance when the impedance is the same. We get a maximum transference of energy. And in terms of an antenna, for example, if I can create a frequency at which my antenna resonates. Well, really what I want to do, if I want to operate on 80 meters, for example, I want my antenna, whatever it is, to be able to be resonant somewhere around 3.5 megahertz. Because then it's radiating out at that frequency, whatever I'm doing, whether I'm talking or banging on a CW key. Okay. So let's take, if you've already watched the inductive and capacitive reactance videos and know those formulas, then you have a pretty good idea. And we're just going to plug a couple of values in. Let's say, for example, I have the R is equal to 22 ohms. I'm just putting it here because that's what's in the circuit, but it's really not used. There's no R in this. And we have the L is 50 microhenries, and the capacitor is 40 picofarads. Okay, these are some pretty tiny amounts. So let's see what we get. Well, first of all, let's write these out because we're going to be using our calculator. Micro is times 10 to the minus 6. So this is going to be 50 times 10 to the minus 6. Pico, and if you're really old enough, you may remember micro, and they've since changed it, fortunately, to pico. This is going to be 40 times 10 to the negative 12th. So it's double that. All right. So all we really need to do then is put this inside parentheses, put this in our formula. So I'm going to start off then with 1 divided by, and I'm going to put the whole denominator inside parentheses. So here's our 2 times pi. No, I hit the wrong button here. 2 times pi times our frequency. Not times our frequency. I don't know why I put an F in there. Silly me. There we go. Thought that was weird. Okay. 2 pi times the square root of LC. So you probably caught that already. So 2 pi times the square root of 50 times 10 to the negative 6 times 40 times 10 to the negative 12. That's the end of our square root. Oops, went one too far. Let's close off our parenthesis and press this. So we see then that our resonant frequency is 3558812. Let's not worry about the 0.7, whatever it is. So this is 3.5 or 3.6, whatever you want to round that off to. Let's just do 3.56 megahertz. So if I had an inductor and a capacitor at this, then this would resonate at a frequency that's right smack there on the 80 meter band. All right. The hardest part, I think, is keying these values in a calculator. And that's kind of why I like to write them out first, so I know what I'm looking at. Okay. Make sure you understand that. And again, there's questions on the extra test that deal with all this resonance and reactance. All right, see you in the next video.